All right, welcome to the screencast for 6.2. So when we studied chapter 5, we went over all these properties of indefinite integrals, and it literally said from chapter 6, so now, surprise, we are back where we started. So the power formula, this is what we've been using heavily so far. So what this is, let's see, if I want to take the integral of x cubed dx, what we do is we add 1 to the exponent, divide by our new exponent, and then we tack on a plus c. Now keep in mind, this is what you can use anytime you have x as the base, except for when you have x to the negative 1, aka when you have 1 over x dx. This is the only time, and then you have ln of u. So this is just ln of x, absolute value, plus c. Alright, because imagine if you had x to the negative 1, and then you try to add 1, you're dividing by 0, what the heck, you can't do it. Okay, cool. The trig formulas. So the integral of cosine is going to be sine, integral of sine is negative cosine, and how we do that is if we take the derivative, literally go backwards, derivative of sine is cosine, derivative of negative cosine is sine, right? Taking the derivative versus the integral. So the main three that I've asked you to know are these three. Really heavily sine and cosine, you should be 100% confident with those. We use tangent enough that you should know it by now. This one pops up a good amount, but you still should know where to find all 6 of these integrals. But the main 3 you should know are highlighted. Alright, exponential formulas. You know, anytime you try to take a derivative of e to the x, it's just e to the x. Anytime you take the integral of e to the x, it's just e to the x. And then our inverse trig formula. So it's a lot of people will try to have an algebraic integral, but 1 over 1 plus u squared is going to be tan inverse of u. Alright, so this is just the tan inverse and sine inverse. We went over those as well when we were taking derivatives. This is one reason I had seniors do all the review of derivatives, because I want you to be used to seeing what the derivatives are for common functions, because we have to apply it. So recall how we find the derivative of composition of functions. Remember, composition of function is you have one function inside another. So here we have e to the x, but secretly in place of x we have 3x. So 3x is a function, e to the x is a function, so if I subbed in 3x into x, in my 3 to the x it's a composition, literally a function inside a function. So if I want to take the derivative, this is just e to the 3x and then times 3, because this is chain rule. Right? Throw back to chapter 4, chapter 3, whatever, when we first learned derivatives, chapter 3. Here, another way to write ln squared of x is going to be ln of x squared. So first thing I write is 2 times ln of x to the first power, then I must multiply by the derivative of what's inside, which is ln of x. So this is just going to be 2 ln of x over x. All right, remember, we're taking the derivative, Here, take the derivative of the outside function, so derivative cosine is negative sine, and then you have x squared inside, and then you have to multiply by the derivative of x squared, which is 2x. So overall, we'll have negative 2x sine of x squared. So these are taking derivatives of composite functions. Remember, chain rule. Now the issue is, how do we integrate when there's a composition of functions? Right, so here I have sine of 2x. It's not just sine of x. Sine of x will be chillin', but this is actually sine of a function. 2x is a function. Here we have 1 over 2x minus 1. So it's similar to 1 over x. Okay, well we know the integral to that is ln of x. But on the bottom we have a function itself, which is 2x minus 1. Right, we have e to the 4x. Right, e to the x we know how to deal with. But when we have a function inside a function, remember f of g of x, literally a composition of functions, it gets a little messy trying to take the integral. And lastly, this is not just x to the 4th, it's 3x plus 5 to the 4th composition. So how do we actually deal with this? We use the substitution method. It's literally the chain rule in reverse. Let me fix the parentheses. Something like this. Okay. Why does it do this? Okay, perfect. So what I want you to notice is whenever you have a composition of function, right, f of u of x, if we multiply by the derivative of u of x dx, and we're taking the integral. This is just going to be equal to the composition, f of u of x plus c. Oops, plus c. Right? Capital F, not lowercase f, because you have to take the antiderivative of lowercase f. Okay, let's go through this in really slow steps. So, steps for u substitution, aka the chain rule in reverse. So, we let u be the inside function. So, if f of g of x, if we have f of g of x, the u is this inside portion, g of x. So, this first example, I have 4x minus 5 inside the to the 6th power. So, I'll let u be 4x minus 5. Now, I want to take the differential, all right? If u is 4x minus 5, right, du dx, taking the derivative with respect to x, well, okay, take the right side. Derivative with respect to x is going to be 4. If you multiply by dx on both sides, you get du is equal to 4 times dx, which is what this is doing right here. Okay, so far so good. Rearrange and rewrite the integral in terms of u. Now, you should no longer have the other variable, so we're rewriting everything in terms of x. You may also need to compensate for coefficients. Okay, so this whole thing right here, I'm writing as u. And remember, du was literally 4 times dx, so this thing right here is going to be my du. So it's just the integral of u to the 6 times du. Right, remember, instead of saying du, so instead of saying 4 times dx, we're just putting in du. So I'm taking away 4 dx and in place putting du. Then integrate with respect to u. Okay, so this is easy, right? You know this. It's just the power rule. Add 1 to the exponent, divide by our new exponent. So this is just u to the 7 over 7 plus c. It is a indefinite integral. There are no bounds. It's not from, 5 to 6. There are no bounds, so you must add the plus c. Substitute back in the variable. So remember, our u going all the way back up to the top, it was literally 4x plus 5. So 4x plus 5 to the 7th power over 7 plus c is our final answer. Awesome. Do not despair if you're confused, because I have another whole example for us to do. So the first thing you must do is let the u equal inside. So here we have a trig function. It's not quite as easy. All right, so where's my function, right? Which one's inside? Let me see. So this is literally sine of x, but here x is not just x, it's 2x. So I have a function taking sine of a function. So we let u equal 2x. All right, find du. So du dx, take the derivative with respect to x on both sides, which is going to be 2. So du is just going to be 2 times dx. Perfect. 2 times dx. So using my highlighter, 2 times dx. 2 times dx is going to be du. And then we already said u was 2x. So this is just going to be sine of u times du, right? The integral. Because instead of saying 2x, I put in u. Instead of saying 2 dx, I say du. Integrate with respect to u, okay? So if you immediately don't know what the integral of sine of u is, think to yourself, what function, when I take the derivative, is going to give me sine? Okay, so it's negative cosine of u plus c. We sub back in our original values. So it's negative cosine, remember what u was? It was 2x, and then plus c, and then that's it. So it's just one step further than what we did last chapter, right? Composition of functions. So I want you guys to try example 1, pause the video, give it a shot, and then I'll explain it. All right, so here are the parentheses. So, and I tell you what u is, right? These first couple ones, I tell you what u should be. So we let u equal x minus 7. So du is just going to be equal to dx. All right, take the derivative of x is just 1. So it's just du dx is equal to 1. Move the dx over, so du equals dx. Okay, so this is just going to be the integral of u cubed du. All right, power rule, add 1 to the exponent, divide by our new exponent plus c, and then substitute back in our u at the end, and we're good, right? X minus 7 to the 4th over 4 plus c. Try out b, give it a shot before we do it together. So when I take the derivative with respect to x on both sides, I get du over dx is equal to 2. Therefore, du equals 2dx. So from now on, I'm just going to go straight to this step when I take the derivative. All right, let's replace. So remember, du is equal to 2dx, so here's 2 times dx, right? It goes away, that's ideal. So this is just e to the u du. So derivative of e to the u, okay, it's just e to the u plus c. Don't forget, you must substitute back in your u, so e is 2 to the x plus c, and we're good. This next one, not as bad, because I still tell you what u is, right? Later, I won't tell you what u is, and you have to start finding what the inside function should be. So here I said it's x squared plus 1, so here's my x squared plus 1. So I already know this is going to be the integral of the square root of u. Okay, so du is going to be 2x dx. Okay, well 2x dx, that's what my du is. So it's just the integral of square root u times du. All right, let me rewind a moment, right? Remember, I'm just going to rewrite this in terms of in a different order. That way I can see here's my u, here's my du. All right, so I'm just substituting back. I'm substituting these out in terms of u. All right, so this is the same thing as saying the integral of u to the 1/2 power du. Add 1 to the exponent, so u to the 3/2, divide by our new exponent, which is 3/2 plus c. This is going to be 2/3 u to the 3/2 plus c. Plug in our u value, right? Our u was x squared plus 1, so this is 2/3 of x squared plus 1 to the 3/2 plus c. And if you want to know that you got the right answer, take this derivative. Do you get back what you started with? You should, right? When I say you should, 100%, if you do it right, you will get back what you started with. Right? If I take the derivative of what I just boxed, you will get 2x times the square root of x squared plus 1. All right, this one's tricky. I still tell you what you should say u is, so this is u, right? Integral of e to the cosine of x. This is my u, and I'm left with sine x dx. Okay, let's take the derivative. Derivative of cosine is going to be negative sine x dx. Ooh, there's an issue, right? So I only have sine x dx. I don't have that negative. So instead, what I'm going to do is move the negative to their side. So I have negative du is equal to sine x dx. Awesome. So this is going to be equal to negative du. So I have the negative integral of e to the u du. So this is just going to be negative e to the u plus c, right? Because the negative on the outside comes from the fact that there's a negative right here. Integral of e to the u is just e to the u. Derivative of e to the u is just e to the u. Okay, and then lastly, plug back in for u. So negative e to the cosine of x plus c, and then we're good. That's it. Hopefully these are going relatively smoothly. Feel free to ask each other for help. You also can ask Miss Malikian or Miss Kasif if you're like really needing help today, which is Monday when you are supposed to be watching this during class, or I will be back on Tuesday. Cool. Once again, I tell you what u is. So this is my u. All right, du. Du is 3 dx. It's an issue, right? 3x plus 1 to the 4th power. Let's see, I said this inside part was u, and then I just have dx. What am I going to do with this 3? That's an issue. Well, what I can do is make this 1/3 du, right? Divide by 3 on both sides is equal to dx. So that way I put this in place of 1/3 du. So I take the integral of u to the 4th times 1/3 du. Just plugging it nice and slow. I'm going to bring that constant out front. All right, this is one of the properties of integrals. And I'll have u to the 4th times du. Okay, so that's 1/3 times u to the 5th over 5 plus c. All right, plug back in our u, so 3x plus 1 to the 5th, and then on the bottom, 3 times 5 is 15 plus c. Perfect. It's just knowing the chain rule, right? You can take your answer at the end, take the derivative, and you should get back what you started with. Okay. I think that's all I want to say about this one. So notice these last two, when we got du equals blah, 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 it wasn't exactly perfect. So this is what I meant by deal with coefficients. All right, so up here, oops. Where did I talk about it? That's awkward. Okay. Oh. You may also need to compensate for coefficients. That's what I'm talking about. Compensating with coefficients. I have this, this 3. Where the heck? What do I do with it? Oh, I move it to the other side so that way I have a 1/3 du. It's just a number, so we're good. We don't have to mess with it. It's when you get this extra variable. Ooh, that's way more difficult, but we're good. We're chilling right now. Okay, I'll tell you what u is. All right, take the differential. So we're just taking the derivative with respect to x. This is 6x squared dx. Let me rewrite this. Square root of 5 plus 2x cubed. Right, this inner part is going to be my u. And then I have x squared dx. So this is supposed to be my du. Issue is 6x squared dx is du. So if I divide both sides by 6, I have 1/6 du is equal to x squared dx. So this is 1/6. So the integral of, 1/6 the integral of square root u du. Alright, so this is just 1/6. Let's see, u to the, integral u to the 1/2 power. I want to make sure we're good with these powers, so I can just use the power rule. 1/6 times u to the 3/2 divide by 3/2 plus c. So this is, instead of dividing by 3/2, multiply by the reciprocal, so times 2/3. So it's 2/9 u, 3/2 plus c. Plug back in our u, and we will be close to done. Let's see, my u was 5 plus 2x cubed. So the 3/2 plus c, and we're good. That's it. Perfect. All right, and we have more examples. I don't know what I was thinking. Why did I do this? Use substitution to evaluate the integral. Yes. Okay, I see now. I want you guys to try A and B. Go ahead, pause the video, and then I will pop up the solutions for you to look at. All right, so note, I did not tell you what u was. You had to try to figure it out yourself. So based on these previous examples, hopefully you see we're picking the inside function. So I picked the function that was inside the parentheses, right? 2x minus 3. Then I took the derivative, right? I found du. Issue is, I don't have 2 times dx. I only have dx. So that's why I wanted to have the 2 the other side. So I had 1/2 u. So I plug in 1/2 du in place of dx, and then I plug in u in place of 2x minus 3. All right, bring the 1/2 out front, use power rule, etc. I feel like hopefully you're starting to get it. Okay, let's do this one together. So, remember this is the same thing as ln of x cubed. So I need to pick a nice u value. It seems like ln of x was plugged in. Right, so let me say u is equal to ln of x. That means du is going to be 1/x dx. Because remember, we're taking the derivative with respect to x. So if I multiply both sides by dx, that's why I'm getting the dx on the other side. Okay, so right here, that's what it's equal to. That's my du. So this is just going to be the integral of, let me rewrite it. So this is ln of x to the 3rd power, right? So this is my u. Times 1/x dx. This is my du. So integral of u cubed du. That's just going to be u to the 4th over 4 plus c. So that's just going to be ln of x to the 4th power over 4 plus c. Awesome. I want to note a couple things, all right? Saying ln of x to the 4th power, this is the same thing as saying ln of 4x. All right? So saying ln of x to the 4th power, this is not the same thing as writing ln of x to the 4th. All right? This is very important when you're writing that you need to be clear. You will get points taken off if you are not clear. All right, saying over here ln of x to the fourth power, that's not the same thing as ln of x to the fourth, okay? It's almost like there's parentheses here. If you're not going to use parentheses, you have to be careful how you write it. All right, here, let's see if we can pick out the best u. So I see there, it almost looks like this is our inside function, so I can let u equal x squared plus 3. Take the derivative, du is going to be 2x dx. Ooh, I don't have 2x dx, I have 1x dx. So I'm going to say 1/2 du is equal to x dx. So let's rewrite the integral. So we have the integral of 1 over square root x squared plus 3 times x dx. Okay, so notice this is going to be 1/2 du. This right here is my u. So it's the integral of 1 over u times 1/2 du. Perfect. Okay. Ooh, hold on. This is supposed to be a square root. Square root. Ooh. Sorry about that. Okay, square root of u. Perfect. Okay, so we've done something like this before, right? This is just the integral of u to the negative 1/2 power time, let me put the 1/2 out front, du. So add 1 to the exponent. So I have u to the 1/2. Divide by your new exponent, which is 1/2. Dividing by 1/2 is the same as multiplying by the reciprocal, which is times 2. So this is 1/2 times 2 times u to the 1/2 plus c. Those go away. So it's u to the 1/2 plus c. Let's go in, plug back our u value. Our u value is x squared plus 3. And then plus c. This is it. All right. Ooh, tricky trick. Think about what we should plug in. Which one would be more beneficial to be u? So I'm going to let u be the function with the higher exponent, because then du, of course, when you take the derivative, hopefully it'll be the other half. So x cubed plus 3, when I take the derivative, 3x squared dx. Ooh, wait. Oh, plus x. Ooh, no wonder. I was looking at the wrong thing. Plus x. So this is going to be plus 1 dx. This right here is exactly what we have. That's du. Perfect. So this is the integral of u squared du. Alright, so that's just going to be u cubed over 3 plus c. Plug back in our u. Our u was x cubed plus x. I don't know why I said it wrong first. Whatever. And that's it. Cool. Now, there's a shortcut for using the u substitution if the derivative of u is a constant, right? So when we're taking du, right? Notice du, here, this has a variable in it. This du has a variable in it, has an x in it. But if the derivative of our u is a constant, what we can do is just divide by derivative of the inside. All right, so just divide by the derivative of the inside. So notice here our u was 2 theta, so du, the derivative of 2 theta, is going to be 2 d theta. Oh, literally, it's just a number? Awesome. That means I can just take the integral of cosine of theta. Okay, well, let's see. What function's derivative is cosine? Sine. Okay, so I have sine of 2 theta. And then just divide by the derivative of the inside. Okay, so divide by 2. If I try this one, let's see. The derivative of, let's see, our inside function 6x. So the derivative of 6x is going to be 6. So I'm going to take e to the 6x and divide by 6, right? The derivative inside. And then that's it. This is a shortcut for when the derivative of the inside is a constant, meaning no variable, right? Derivative of 6x is just 6. Here, my inside is 4x minus 1. The derivative is 4. Awesome. Okay, solve that 4. Now, just treat it like you had x to the third power. So we add 1 to the top. So this is going to be 4x minus 1 to the fourth. Then you have to divide by your new exponent, which is 4, plus my c. Okay, so that's why I have 4 times 4 on the bottom. This is from the derivative of the inside This second one is from actually taking the integral using power rule. So this is 4x minus 1 to the 4th power over 16 plus c. Awesome. Use substitution with a trig identity to evaluate each integral. Did I want to do this one? No, I'm going to skip it. I feel like we have enough practice so far. We're okay. All right. And lastly, change a variable formula for definite integrals. So it's kind of like a shortcut in a sense. You have a definite integral, not an indefinite, right? So we've been working with indefinite that don't have bounds. Now we have bounds. So what you can do is, okay, we have done something like this before. Okay, so once we write it in terms of f of u, right, the change of variable with my u substitution, all you have to do is plug in your bounds, plug them into our u variable, and then integrate from u of a to u of b. Okay, so what does this look like? I'm going to let u, right, it has to be my inside function, I'm going to let it be x squared minus 4, right? It's just this part right here. So that means du is going to be 2x dx. I have x dx, not 2x dx. Oh my god, it's like we did this problem already. Pretty sure we did. Okay, so I gotta get that 2 to the other side. Gotta fix my coefficients. Divide by 2 on both sides. Now I have 1/2 du is going to equal is equal to x dx. Okay, so I can write the 1/2 out front, have my integral. Let's see, I said my u, so this is 1 over u du. So I have, most of the function part. Now I have to figure out the bounds. So what you do is you plug in your bounds into the u. So u of 0, well, plug 0 in here, and you get -4. All right, we're going from -4. If you plug in our top bound, u of 1, 1 minus 4 is -3. Okay, step by step. Here we go. So this is going to be 1/2 of ln of absolute value of x, evaluated from -4 to -3. Integral of 1 over u is just ln of u. Yikes. Sorry. Ln of absolute value of u. Okay. And then when you evaluate definite integrals, you go from, you have your lower bound, you have your upper bound, etc. And the reason, this is a big reason why we have the absolute value in this integral is because if we can't plug negative values into our into a log function. Okay. So it's 1/2 upper bound, ln 3, minus the lower bound, ln 4. But wait, we're not done. Ready? Using our properties of logarithms, this is going to be 1/2 ln of 3 over 4. But wait, there's more, right? The power property of logarithms. This is going to be the same thing as ln of the square root of 3/4, right? Because it's the 1/2 power. We're not done. Once again, this is ln of square root 3 over 2, because square root of 4 is 2. And then we are done. And see, there's no c, because this is a definite integral. We have bounds, so there's no plus c at the end. We're going to do another example. So, you're watching this in class. You always can pause and go back. That's the beauty of screencast. You can pause, rewind as many times as necessary. All right, let's go step by step. Tan x, secant squared x dx. Okay, so what should be our inner function? We could have secant squared x, but then we take the derivative of secant squared. Ooh, that's going to be a chain rule. So let me have u be tan x. Okay, when I take the derivative of tangent of x is secant squared x and then dx. This is exactly what we have. So this is just the integral from integral of u du. We have to figure out our bounds. So u of 0 is going to be tangent of 0. Well, it's just 0. Wonderful. U of pi over 3, so I'm plugging these in to this function, is tangent of pi over 3. Pi over 3 is 60 degrees. Tangent of 60 degrees is going to be root 3. So one thing I forgot to note is once you have it in terms, you change your bounds so they're in terms of u. So I don't have to go and plug back in my function. Now you can, right? So as soon as I have my bounds, okay, cool. You add 1 to the exponent, right? So u to the first plus 1. This is going to be u squared over 2. Evaluate from 0 to root 3. You can go back and plug in terms of x, but I have the bounds in terms of u, I have the function in terms of u, so there's no need. We're chilling now. Root 3 squared over 2 minus 0 is just going to be 3 over 2. We're chilling. We're good. I did not have to go back. Since everything's in terms of u, my bounds I plugged in to u, so we're good. That's what this upper part here is saying. Right? You can leave your function in terms of u because you changed your bounds to be in terms of u. All right, and that is the end of this lesson. Good luck with homework.